Welcome to Ask and Learn.
In Part A, we are given a differential equation with an initial value, and we are asked to use Euler's method to approximate the value of a function y at point 4. Differential equation is y prime equals y. Initial value is y of 0 equals 1. In Part 1 of Part A, we are asked to approximate y of point 4 given step size h of 0.4. So, using Euler's method, we have that y of 1 is equal to y of 0, which is the same thing. Y0 is the same as y of 0, or 1, plus a step size h times our function y evaluated at the point 0, 1, which is simply 1. This is equal to 1 plus 0.4, or 1.4. y2 is equal to y1, which we have as 1.4, plus our step size, 0.4, times okay, so we don't need to do y of 2, because y of 1 is already an approximation for y of 0.4, since we moved from 0 to 0.4 plus step size of 0.4. This is approximately equal to y of 1, which is equal to 1.4. So answer for part 1. In part 2, you're asked to approximate this value using a step size h of length 0.2. And we see that again, y1 is going to be equal to y0, or 1, plus the step size, 0.2, times our function y evaluated at the point 0, 1, which is just 1. This is equal to 1.2. And in order to get from x equals 0 to x equals 0.4, we need to add another step. So we have y of 2 is equal to y of 1, which is 1.2, plus the step size, 0.2, times our function y evaluated at the point 0.2, 1.2, and this is going to be times 1.2. This is equal to 1.2 plus 0.2 times 1.2 is 1.44. So we see that if this step size y of 0.4 is approximately equal to y of 2, which is equal to 1.44. There's our answer for part 2. In part 3, we are asked to use a step size of 0.1. There will be 4 steps. So y1 would be equal to y0 is 1 plus the step size, 0.1 times the function y evaluated at the point 0, 0.1, or 0, 1, which is just 1. So this is 1 plus 0.1, or 1.1. Second step, y2, when the value is going to be y1, which is 1.1, plus our step size, 0.1, times the value of our function y at the point 0.1, 1.1 is simply 1.1. This is equal to 1.1 plus 0.1 times 1.1 is equal to 1.21. y3 is equal to y2, or 1.21, plus our step size times the value of the function y at the point 0.2, 1.21, which is going to be 1.21. And this is equal to 1.331. And finally, for our last step, we have the value y4 is equal to y3, or 1.331, plus 0.1 times the value of the function y at the point 0.3, 1.331, gives us 1.331, which is equal to 1.4641. And so we have that y of 0.4 is approximately equal to y4, which is equal to 1.4641. This is our answer for part 3. In part B, we are given the exact solution of our initial value problem. We are asked to draw the graphs of the solution using our Euler approximations. And then we're asked to evaluate whether or not our approximations are under or over estimates of the true value. So we're given that the solution to our initial value problem is y equals e to the x we're asked to draw this from 0 to 0.4 on the x-axis. Now we know this is all going to be in the first quadrant, so I'm only going to draw the first quadrant. And I'm going to make this as detailed as I can, because otherwise this isn't going to be very useful. So I'm going to make the largest value on the x-axis going to be 0.4. So we also have 0.2 here, 0.3 here, 0.1 here. This is 0. In the y direction, you have that just draw this table of values here quickly. 0.4, b of 0.4 is going to be 8 to the 0.4 is approximately equal to 1.4918. This is very, very close to 1.5, so I'll just draw 1.5 here on the graph. The max value on the y-axis. This will be 1.0, and this will be 0.5. And I'll graph our solution here in black. So we know, for instance, that e to the 0 is 1, so we have a point at 0, 1. We also have a point at 0.4 and just under 0.5. This is exponential. Let's draw some more points to make sure we get the right curve. So at 0.1, if e to the 0.1 is 1.105, so about 1.1. For 0.2, we have that e to the 0.2 approximately equal to 1.221. So a little over 1.2. I think with these points it's going to be easier to draw a function. So with this graph, it looks almost like a straight line, slightly curved. And using our different step sizes, I'm going to graph our Euler approximation from part 1 in red. So we have from this that one point on this approximation is of course the initial value 0, 1. Another point on this approximation, we have that x1, y1 is equal to 0.4, 1.4. We know it's going to be less than the function. So we see that this is going to consistently underestimate the real value of the function. Graph our function from part 2. I'm going to graph it in green. So we have that again, point y, x0, y0 is the point 0, 1. And we have that the point x1, y1 is going to be the point 0.2, 1.2. So 0.2, 1.2. Definitely closer than our estimate from part A. And then x2, y2 is equal to 0.4, 1.44. Is in between. Connect these to piecewise linear function. It's pretty hard to see, but our estimate from part 2 seems to be still underestimating our solution, but it is a better estimate than our estimate from part 1. And finally, to graph our estimate from part 3, I'll draw this in blue. We have again that the point 0, 1 lies on this estimate. We also have the point x1, y1 is the point 0.1, 1.1. So better approximate the solution than the graph parts 1 and 2. So we see that they all underestimate, but they get progressively better. In part C, you're asked to find the error in Euler's method. You're given that the error in Euler's method has this formula. Error is equal to the exact value minus the approximate value from our Euler approximation. So this error can be positive or negative, and the sign will tell us about whether we are over or underestimating the value of the solution. And you see that in part 1, where we said the step size h was 0.4, the error is, I'm going to approximate e to the 0.4, 1.4918 minus our approximate value for y of 0.4 was 1.4. This is equal to about 0.0918. In part 2, we said the step size is now 0.2, and our error is going to be 1.4918 minus our approximation of y of 0.4, which we said was 1.44. This is equal to even these errors are actually approximations. This isn't the true value of e to the 0.4. This is equal to 0.0518. And finally, in part 3, where we said the step size was 0.1, our error is approximately 1.4918 minus 1.4641, which is equal to 0.0277. So we see that we have these three calculations for the errors: 0.0918, then 0.0518, and 0.0277. And we see that if we take the ratio of these errors, so 0.0918 over 0.0518, this is approximately equal to 1.8 and 0.0518 over 0.0277 is approximately equal to 0.19 So you see that as the step size h is halved, the error, well, you see that not only as it decreases, by about a factor of 2. So the